The Riemann sums we did before all had the exact same size rectangles. That's not a requirement in order to find a Riemann sum. Certain cases, it's going to be better to have different sized rectangles. One such case is when you're dealing with roots. So I'm going to use a third root and show how different sized rectangles will make finding this Riemann sum easier. So if I want to find the area under the curve from 1 to 3, that's a total distance of 2. So instead of dividing 2 by n, I'm going to divide it by n cubed. Okay, and the reason I'm going to use n cubed is because I'm going to have to take the cube root. So when I go to plug in values, I want to be able to take the cube root of it. So this is what I'm going to divide my 2 into, n cubed pieces, which is just another form of n. Since n is an arbitrary amount, this is still just like an n, but now that it's cubed instead of just being n, it's going to make solving easier. So if I'm dividing into n cubed, I can also pick the cube of the ith rectangle to talk about. Instead of just the ith rectangle, I can pick the cube. So I'm going to use right endpoints. So this would be the location of, so let's see, I want to go from 1. So I guess I should move these rectangles over. Okay, but if we were going from 0, this would be the first rectangle. Okay, so this point here would be this is the first rectangle, so it's 1 of my n cubes over. Okay, and really I'm going 1 cubed. Here would be 2 cubed of my n cubed over. This would be 3 cubed of my n cubed. All right, so when I get to the ith rectangle, this right endpoint is going to be 2 times I cubed over n cubed. This left point is going to be the height of the previous rectangle. Okay, so if this is the ith, this would be the I minus 1 rectangle. Okay, I want to cube that. Don't forget the 2 over n cubed. So our delta x, which is our width, so the width of our ith rectangle is going to be the difference between these. Okay, so I'm going to take this one and subtract that one. So it's going to be 2I cubed over n cubed minus 2 times I minus 1 cubed over n cubed. So now if we simplify this, I'm going to cube this out. So I'm going to use Pascal's triangle. Okay, so this is my coefficient of the first term, and I gets all of the powers. Okay, this is the coefficient of my next term, the 3. I gets 1 less power, and the negative 1 gets 1 power. My next coefficient is 3 again. I gets 1 less power, negative 1 gets 1 more power. 1 is my coefficient, I gets 1 fewer power, so there's none, and negative 1 gets all of the powers. So this simplifies to be I cubed minus 3I squared plus 3I minus 1. And then we multiply all these by the 2 that's sitting out here. So let's just fill in what I have so far. Okay, so now if I'm going to distribute the minus and the 2. Okay, since I have a common denominator, I can put them all over just n cubed. So then I'm going to have minus 2I cubed plus 6i squared minus 6i plus 2. These cancel out, and so my width, my delta x, so my width of my ith rectangle is 6i squared minus 6i plus 2 over n cubed. Okay, that's my width. So a function at this rectangle, which is the height. Okay, so this is the height, this is the width. So the height is going to be the function at this value. So if I put that into my function being the cube root of x, okay, so I'm going to have the cube root of 2i cubed over n cubed. Okay, so that's f at ci. This is my delta x sub I. So I need the limit as n approaches infinity of the sum from 1 to n of my height. Okay, if I can simplify this, this would just, oh, this is the cube root. This would just be the cube root of 2. Okay, the cube root of I cubed is I, and the cube root of n cubed is n. Okay, so the only thing in the cube root now is the 2. So I'm going to have cube root of 2 over n I. Okay, and then that gets multiplied by my width, which is 6i squared minus 6i plus 2 over n cubed. So I can multiply these. So let's have this I be up here. So I can distribute that inside. So I'm going to have 6 times the cube root of 2 I to the third over n to the fourth. Okay, that'd be the first term here. And I'm going to split my sum up also. It'll be minus, okay, because that minus sign. I'd have 6 times the cube root of 2 I squared over n to the 4 plus the sum of 2 times the cube root of 2 over I over n to the fourth. Alright, so now if we take our constants out and change our I cubes, or our I values into n's, okay, so all of this stuff is a constant, so I'm going to have that out in front. Okay, and then I cubed, the sum of I cubed turns into n squared, n plus 1 squared over 4. Here, all this stuff comes out, so 6 cube root of 2 over n to the fourth, and I squared turns into n plus 1, 2n plus 1 over 6. And this, all this comes out, so we've got plus 2 cube root of 2 over n to the 4, and I turns into n plus 1 over 2. Alright, so let's reduce a little bit before we start simplifying. Those two n's will cancel 2 on there. I can reduce this to 2, and that makes this a 3. These 6's will cancel. This n will cancel one of these and make that a cube. This n will cancel one of these and make it a cube. These 2's will cancel. So now looking here, I'm going to square this out. So that'll be n squared plus 2n plus 1. And on the bottom I've got 2n squared. Over here I've got The cube root of 2. This squared out is going to be 2n squared plus 3n plus 1 is over n cubed. And here I've got cube root of 2. Okay, I'm going to distribute that in, so it's n plus cube root of 2 over n cubed. Now, if we start looking here, I could distribute this in, all right, and then I could break up each term so it's got an n cubed underneath. But if you notice, each one is going to have more n's on the bottom than it will on the top. The limit of this term entirely as n approaches infinity is 0, so I can get rid of the whole thing right away. This one, this part of it will go to 0, and this part will go to 0. Okay, and these will cancel and leave just this fraction. And here, both of these will go to 0. So as I take the limit, I end up with just this piece, and that's the area that I have underneath the curve. So the big difference is just finding the width of your ith rectangle. Okay, just using, I mean, this is pretty much just a notation thing, because we know that if we cube things, it'll be easier to cube root them. I cubed, since I doesn't really have any meaning, I cubed could just be some other I, but it's easier to think of it as an I cubed so that we can cube root it.